Hello, my name is Harrison Budker, and today I will be presenting Lab 3, Black Hole Orbit. In Lab 3, we were asked to find the mass of a black hole after being given the x and y coordinates of a star orbiting the black hole. We were also given the star's mass, the time interval between each position data point, and the position of the black hole. After editing the Lab 3 starter code and analyzing the star's motion, I discovered the mass of the black hole to be 3.3480 E31 kilograms. In order to find the mass of the black hole, I first started from a fundamental principle. The momentum principle states, the final momentum is equal to the initial momentum plus the net force times change in t. Another way to write this is the final momentum minus the initial momentum equals F net times change in t, and then the change in momentum is equal to F net change in t, and then change in p over change in time is equal to F net. When t is small, the change in momentum over the change in time is approximately equal to the derivative of the momentum. Since we know that the vector momentum is equal to the magnitude of momentum multiplied by the position vector of momentum, we can use calculus and find that dp over dt is equal to the derivative of the magnitude multiplied by the position vector of momentum plus the magnitude of the momentum multiplied by the derivative of the position vector. Since we know that the derivative of the magnitude of momentum multiplied by the position vector of momentum points parallel to motion, and that the derivative of the position vector times the magnitude of momentum points perpendicular to motion, we can conclude that the derivative of momentum equals dp over dt parallel plus dp over dt perpendicular. Since the change in momentum over the change in time is approximately equal to the derivative of momentum when the change in time is small, we can conclude that the change in momentum over the change in time is equal to the change in momentum over change in time parallel plus the change in momentum over change in time perpendicular. This is extremely important for our lab. Now that we understand these physics principles, we can edit our Python starter code to help us see the motion of the star orbiting the black hole, but more importantly to help us calculate the net force. While I am going over the code, feel free to pause the video at any time. I first made the black hole's position my origin. I then added the mass of the star and the time interval between data points. To find the velocity, I used a while loop that found the change in position between every two position points and then divided the difference by the change in time. Once we had the velocity between every two position points, we found the change in velocity and the change in momentum, which was just the change in velocity multiplied by the mass of the star. From there, I translated the physics concepts that I already went over into the VPython code. This would be a good time to pause if you wanted to analyze the code in more depth. Here's what the star orbiting the black hole looks like. The second output number is the magnitude of F net, which is 5.3 E27. We know that because it says it right here. Since the only force acting on the star is the gravitational pull from the black hole, we can make F net on the star equal to the gravitational pull between the star and the black hole. We know F net, we know the mass of the star, and we know the magnitude of the distance between the last position point of the star and the position point of the black hole. That leaves us with one unknown, the mass of the black hole. This mass turns out to be 3.3 E31 kilograms. What does it mean? How are the F net parallel, F net perpendicular, and F net different from change in P over change in T parallel, change in P over change in T perpendicular, and change in P over change in T? As I stated before, change in P over change in T is approximately equal to the derivative of momentum when the change in T is relatively small. So, change in P over change in T parallel is approximately equal to dP over dt parallel, and change in P over change in T perpendicular is approximately equal to dP over dt perpendicular. In general, we would want to take the derivative of momentum to find F net because this will give us a more accurate answer, but if the change in T is small, which it is in this lab, we can just use change in P over change in T to find F net. What if? Suppose a different black hole was placed in the same location and the observed motion of the star remained unchanged. Also, the F net on the star is the gravitational force by the black hole. Would the mass of the new black hole be different? Since the motion of the star remains unchanged, delta P over delta T will remain the same. And remember, delta P over delta T equals F net. And since the only force acting on the star is the gravitational pull from the black hole, we can make F net on the star equal to the gravitational pull between the star and the black hole. Thus, F net, the universal gravitational constant g, and the mass of the star and the distance between the star and the new black hole will remain the same. So, the mass of the new black hole will be the exact same as the mass of the old black hole. Thank you.